In this third and final episode of this series, we'll focus on the Clintonville Substation building itself, and in particular, understanding how it worked and how it functioned as a substation.
To begin, we can consider a substation building such as Clintonville as a black box, so that we can think about its inputs and outputs. We know that its primary function was to convert high voltage alternating current to continuous direct current in order to power the electric trains on the railway. And just like household AC to DC converters, which you likely have several of in your home, we would expect the substation to have ports or interfaces for both AC and DC. The household converter in the US typically has two prongs for an AC interface, connecting to a 110-volt single-phase AC power supply, using 60 Hz or 60 cycles per second of oscillating current, which is based upon two wires, a hot and a neutral. The railway substation, on the other hand, was connecting to a 26,000-volt three-phase AC power supply with 25 Hz current, which was based upon three wires. So we would expect to see one three-pronged interface on the Clintonville Station as the input for the AC current input.
For the direct current output, the household converter uses two wires, a positive and a return or ground wire, that typically connects to a round plug interface, with one wire terminating on the center of the plug and the second wire terminating on the outer ring of the plug, a plug which is typically providing 1.5 to 12 volts of DC power to some household device. The Clintonville substation output was 600 volts of direct current, also with a positive and a return, and so we would expect at least one two-wire interface on the Clintonville substation.
The substation also had a few other functions. For example, it forwarded high-voltage AC current to the Elgin substation on Riverside Drive further up the line, and so it would have switched that current through the Clintonville substation. By switching, we mean that the substation had the ability to turn it off or on for maintenance and isolation of electrical faults along the Elgin line. Likewise, we know that the Clintonville substation forwarded high-voltage AC current to the Elgin Belvedere line, also switching the current within the Clintonville substation. Both of these would have required an external three-wire connection coming out of the Clintonville station. We also know that local farmers and businesses were served power by the Clintonville station, and specifically, we know that it was AC power, but almost certainly not at 26,000 volts, but instead with 450-volt three-phase AC power. This would have necessitated a lower voltage three-wire AC interface coming out of the Clintonville station. Finally, we know that the Clintonville station was providing power to the Fox Valley trolley system, as well as the Elgin City trolley system. What we don't know is whether this was AC power being delivered to a substation on those lines, or whether it was DC power directly connected to their overhead wires and third rails. Depending on whether they were fed AC or DC, these railway lines would have been served with a separate three-wire AC interface or a two-wire DC interface coming out of the Clintonville substation.
Knowing that, if we look at the exterior of the Clintonville station today, we can see multiple external electrical interfaces. On the east side of the wire tower, we can see two sets of three-wire connectors on both ends of the tower. There may have been a middle set in the early days of the substation as well. The southernmost set was very likely the high-voltage three-wire input into the Clintonville substation, coming from the Ingleton station and originating at the Batavia power plant almost 12 miles to the south. The northernmost set of three high-voltage connectors likely forwarded the AC current to the Elgin substation further north along the railway line. So that accounts for two of the external connections.
If we come around to the back of the building, we can see multiple external electrical connections. There are three three-wire interfaces and one two-wire interface. One of the three-wire interfaces was likely for the low-voltage AC supplying the local farmers and businesses, possibly the three pipes, as that may have been an okay treatment for the lower voltage AC. Another three-wire interface was likely for the Elgin Belvedere line, which would have been a high-voltage 3-wire interface destined for the northwest corner of the city of Elgin. It's then possible that the remaining 3-wire interface was for the Elgin City Trolley, or possibly the Fox River Valley Trolley system.
But there are a few remaining problems to solve. First, we don't yet know exactly which interface served which customers or railway lines, particularly on the back of the building. Second, although there is a single 2-wire DC connector coming out of the back of the substation, and you might say, that must have been the output to power the Aurora, Elgin, and Chicago's Elgin line. That may be correct, or it may not. Joe Montilla of the VMRA has aptly observed that there was some sort of structure built around this DC output terminal, as there remain ghosts of an old timber structure outlined on the west wall of the substation, and that is very suggestive, and so it could indeed be case closed. On the other hand, it does seem odd that the railway engineers, who were otherwise ruthlessly efficient, would process the electrical current from west to east through the building, then send it back west out the building, then up and over the tracks, and then down again underground to connect to the third rail. As we'll see, that tended to violate one of their design principles. Nor do we see this 2-wire interface on the back of the Ingleton or Prince Crossing station, to the southeast along the line, which one might expect if it was typical to pass the DC out the back of the substation building. And so there may as yet be an undiscovered 2-wire interface, somewhere towards the front or east side of the building, perhaps below grade, which would have allowed a simpler connection to the Elgin Line third rail.
Returning for a moment to the household AC to DC converters. As many of our viewers may have observed, when these devices are plugged into an AC outlet, they are warm to the touch. That's instructive because it tells us that one of the byproducts of the AC to DC conversion process was heat. And when you scale up to converting 26,000 volts of electrical power, you will unintentionally produce enormous amounts of heat as a byproduct. And as we'll find, that was definitely something that the designers of this substation had to deal with. Designers such as the AE&C chief architect, Charles J. Jones, and electrical engineer, Ernest Gazenbach.
In addition to the inputs and outputs, including the unintended heat production, the designers of these substations, built in 1902, were guided by a set of principles which were becoming well established by this time, as a result of 10 or more years of maturing electrical substation technology. There were essentially 7 design principles that would have guided them, and we should be mindful of these as we continue our examination of the building. Principle number 1. The path of energy is to be as direct and as short as possible from the high-voltage transmission lines to the continuous current feeders. Number 2. The wiring is to be as little exposed as possible and yet be readily accessible. Number 3. All the machinery is to be on the same floor as the operating control panels. Number 4. The principal machinery is to be under the direct control of the operator while standing at the operating control panels. Number 5. All apparatus and machinery are to be arranged so that the effects of an accident shall be confined to the place where it occurs. Number 6. The risk of accident to the operator is to be as slight as possible. And number 7. Substations are to be fireproof.
To find out more about how the building functioned, let's follow the path of the electrical current into the building. We'll start at the top of the building, in what they refer to as the wire tower, as that is where the transformation of energy in this building starts.
The 3-wire high-voltage feeder lines coming from Ingleton and the Batavia powerhouse to the south arrived at the Clintonville Station via a series of 40-foot-tall utility poles, spaced about 80 feet apart. Directly in front of the Clintonville Station, across the tracks, would have stood a 40-foot-tall strain tower, the sole purpose of which was to relieve the strain on the wires as they made a right turn and ingressed into or egressed from the substation. The 4/0-gauge aluminum high-voltage wires passed into the Clintonville wire tower via 3 large ceramic insulators.
Once inside the tower, the first step was to protect the substation against lightning strikes, which were a high risk as the utility poles all along the railway lines were potential targets. So the substation needed to ensure that such a strike did not destroy the expensive wiring and machinery within the building. They needed something similar to a household surge protector, but again scaled up to substation size. These lightning arresters, as they were called, were mounted on the face of the wire flues, the chimney-like wire conduits that passed to the lower floors of the building. We saw the wooden mounting brackets for these lightning arresters on the northernmost wire flue of the Clintonville substation when we examined the interior of the cupola in the first episode of this series.
The 3 high-voltage wires then passed through 3 ceramic pipes, spaced inside the interior of the wire flue, which routed the wires down, not to the main floor, but to the basement, where almost all of the wiring for the substation was maintained. Recall principle number 2, where all wiring was to be as little exposed as possible. And in actuality, there was virtually no wiring on the main floor, where the human operators, the powerhouse men, worked most of their craft.
The basement of the substation was not simply a storeroom or utility room for the substation. It was a vital and integral part of the design. It housed all of the infrastructure for the substation wiring, and it was the principal means by which the heat-producing machinery on the main floor was kept cool, by air cooling. The basement was effectively designed to be airtight. Large blowers on the first floor pushed air from outside the building into the labyrinthine basement, maintaining a positive air pressure in the sealed basement. That positive air pressure was then pushed up through large holes in the main floor directly underneath the substation machinery, bathing the machines in a continuous stream of air cooled by the lower temperatures of the earthen basement. The various aisles within the basement could enable operators to seal off different parts of the basement in order to regulate airflow.
And remember those strange and mysterious brick structures along the west face of the building, beneath the wire flues that we saw in the first episode? If we didn't know better, we might be tempted to speculate that the substation was housing a bread factory with a lineup of bread ovens. But instead, those brick structures were a vital part of the wiring infrastructure for the building, and were referred to as the bus bar compartments. The 3 high-voltage wires that came down from the wire tower through ceramic pipes entered the basement through an opening in the flue. Each of the 3 wires were then terminated on one of the 3 bus bars, each bus bar being contained within one of the 3 levels within the brick structure, and stretching almost the entire length of the building. The bus bar itself was bare number 2 copper wire, a little more than 1/4 of an inch thick, or almost 70 millimeters. From this bus bar, then, connections could be made along the length of the bus bar corridor to the various devices and machines within the building, or to external outputs, such as forwarding the high-voltage AC to other railways.
The high-voltage AC connections to the bus bar were accomplished via motor-driven oil switches, which were housed in brick structures on the main floor, but connected via linkages to the bus bars in the basement. Throwing a manual jackknife switch on a high-voltage circuit would be extremely hazardous, not only for a human operator, but also for the switch itself, as the high potential of the AC current would almost certainly arc through the open air as the switch handle was folded down. This occurs because air does conduct electricity, albeit poorly. To prevent this arcing from occurring, substations utilized motor-driven oil switches, where the connecting elements were bathed in insulating oil, which safely suppressed the arcing until the desired connection was made. The motor-driven movement of the switch also removed the human operator from having to be near or touching the dangerous connection. Furthermore, situating the oil switches in front of the substation machinery enabled operators to cut the current to the machinery when performing periodic maintenance.
Once connections were made with the oil switch, the high-voltage wires would then be carried through the large openings in the wall opposite the bus bar compartments, one opening for each wire, likely guided by ceramic insulating connectors. The wires would be connected to the basement floor to the AC transformers on the main floor, via openings directly beneath each of the transformers. Once the transformers stepped down the high-voltage current, the lower voltage AC would then be transferred through the basement walls via 6-wire ceramic conduits to the massive rotary converters above, which would then complete the conversion by changing the AC current to continuous direct current.
The narrow passages we find in the basement also played a vital role in shoring up the building, as they created shortened spans for the main room's concrete floor to carry the substantial weight of the conversion equipment above. It must have been an incredible experience to stand beneath the rotary converters as they spun at 1500 RPM while in full operation, roaring, humming, and vibrating the entire building.
Passing up to the main floor, we find ourselves in the primary business portion of the substation, in what was known as the rotary room, in deference to the huge rotary converters which dominated the space. When the station was built in 1902, there were 10 large arched windows providing light and ventilation for this room, 3 windows on the north and south ends, and 2 windows on each of the east and west faces. All of these main floor windows were operable and could be opened by rotating the bottom sash vertically.
The only 2 exterior doors to the substation were situated on the east side of the building. The entrance on the southeast corner was covered by a large 14-foot by 15-foot wooden awning and served 2 purposes. Most of the time it was the entrance for the waiting area, where passengers could get in from the elements and possibly where tickets could be purchased. There was almost certainly some sort of partition that would have kept the passengers from wandering near the dangerous machinery within the rotary room, likely similar to the current size of the VMRA's kitchenette, a cinder block room that the VMRA added in the 1960 timeframe. The wooden partition that provided for the waiting area doorway could also be entirely removed by design, revealing a 10.5-foot wide by 9.5-foot tall opening, which was necessary when bringing in or removing the extremely large equipment housed by the substation.
The doorway on the northeast corner of the building was a service door with an arched window overhead, and which would have provided a substantial 5-foot wide by 7-foot tall opening, suitable for almost all of the day-to-day operations and maintenance of the facility. In the early days of the railway, there was also likely a full stairway to the basement immediately to the right of this entrance, which provided easy access to the labyrinth below, as evidenced by the 4-foot by 9.5-foot floor cut in the main floor, which can be seen from the basement below to this day. The opening for the stairway may have been filled in later, with only a scuttle hole access to the basement via a ladder.
Entering the rotary room from the southeast, from the passenger waiting area, to our left on the west side of the building, we can see brick structures fronting the wire flues, which housed the array of oil switches, and that enabled operators to turn on and off the various circuits which entered and exited the Clintonville Station. Recall that the oil switches were the first piece of equipment that the high voltage lines would have traversed coming into the station. Doing all of the current switching on the high voltage side of the substation was somewhat revolutionary at the time, as switching was typically done once the current had been stepped down. But the AE&C design leveraged oil switches to safely manage the high voltage switching, which is actually the better place to do the switching from a maintenance point of view. The motors which drove the oil switches were DC powered, from current coming out of the rotary converters. When the rotary converters were down, or turned off, however, the switch motors could still be operated via a single 125-volt storage battery. This battery was initially kept within the rotary room on the main floor, but it was eventually moved to the basement due to the acidic fumes emanating from the battery.
To the right or east of the oil switches were the transformers. These were General Electric Air Blast 25 Hz, 26,000 volt to 450 volt AC transformers, weighing more than 3 tons per unit. There was one set of 3 transformers to supply each 500 kilowatt rotary converter. As mentioned, these transformers were air-cooled, with openings in the floor directly beneath the machinery blasting up chilled basement air. Coming out of these transformers, the AC current had been stepped down to 450 volts, 3-phase at 25 Hz, destined for the next step of conversion to continuous direct current via the rotary converters. However, at the Clintonville substation, some of this 450-volt current was siphoned off and sent externally to provide AC power for local farmers and businesses along the railway line in Elgin and South Elgin.
The two massive rotary converters to the east of the building were also General Electric equipment. Each substation was designed to hold up to 3 of these converters, each generating 500 kilowatts of continuous direct current. The Clintonville station always had at least 2 of these 500 kilowatt converters, possibly sometimes having 3 units during the heaviest workloads around 1910. These converters were based on a 6-phase alternating current, spun at 1500 RPM, and weighed 20 US tons apiece. It's no wonder that the main room's concrete floor required additional brick walls in the basement in order to carry the weight.
Rotary converters were invented in 1888 by Charles S. Bradley and were commonly used in electric railways and trolleys from then until the 1920s, when mercury arc rectifiers with no moving parts became the norm. Rotary converters are essentially an induction motor powered by the input AC, which spins an armature with wire windings within a magnetic field, which generates a direct current. Rotary converters were of course a bit more complicated than that, and could also synchronize their speed with the oscillating 25 Hz alternating current so as to provide some degree of pulsing direct current as well. It wasn't the most elegant or efficient of designs, but the motor and generator technology was well known and straightforward, and thereby easier to maintain, and so became ubiquitous throughout the railway industry. Substation operators had to periodically shut down the rotary converters and lubricate the slip rings used on the armatures. And the enormous size and weight of the converters did require some major design, operational, and logistical considerations. You can still see a similar rotary converter today at the Illinois Railway Museum in Union, Illinois.
Positioned in front of the transformers was 1 or sometimes 2 75 kilowatt reactive coils, recognizable by their rounded corners and the top control panel with a large retro knife switch. The reactive coils helped with the regulation of the line voltage between the transformers and the rotary converters by synchronizing the oscillating current, and the panel mounted on top was used for starting the rotary converter. Wiring for this reactive coil and starting panel came through an opening in the concrete floor, where it was again cooled by the positive flow of basement air.
Along the north wall of the substation stood the substation control panels, also known as the switchboard. Each of the vertical panels in the switchboard controlled a circuit within the substation, with the high-voltage AC panels to the left, the AC side of the rotary converters to the middle left, the DC side of the rotary converters to the middle right, and the outgoing DC feeder circuit panels to the far right. Typically, the AC and DC panels were separated by a blank panel. There would have been a separate AC panel to the left for each incoming and outgoing high-voltage circuit. Each of the control panels in the switchboard would have been equipped with ammeters, voltmeters, and indicator lamps for monitoring the circuit, and relays and switches for managing the circuit. All of the wiring for the switchboard once again came in through an opening in the main floor, beneath and behind the panels.
In the northwest corner of the rotary room were 2 3-horsepower Buffalo Forge blower motors. Only one blower was operating at a time, with the second blower being available for backup or maintenance, a cold standby. These blower motors were positioned next to the large 4-foot-wide circular vent on the west face of the substation, where they would take in the external air through the vent and push it at high volume into the airtight basement below, via openings in the main room floor directly beneath the blowers. The air would be chilled to some degree by the cooler temperatures of the subterranean basement, before being pushed up through the openings in the main floor for the transformers, rotary converters, and oil switches, thereby keeping them immersed in a stream of cooler air. Due to the large vent opening in the west wall, the northwest corner was not likely a favorite haunt for the operators, especially in the winter months when it would have been a chilly space. But the heat from the transformers and rotary converters must have kept the overall substation temperature reasonable in the late fall, winter, and early spring.
What also helped with the substation temperature regulation was the wire tower or loft on the west side of the substation. In the heyday of the substation, the wire tower was a much brighter and airier place to be, with 2 windows on the east and west faces, and 1 window apiece on the north and south faces. We saw these north and south windows entombed under a brick veneer in the first episode of this series. These arched windows all opened by turning horizontally on pins set into the sash. On warmer days, the wire tower windows would have been kept open to enable warm air from the main floor to pass up and out of the building. Although a small scuttle hole is the only access to the wire loft today, it is possible that originally the wire tower had no flooring, but was instead open to the main floor below, providing even more light and ventilation to the substation.
Back outside of the substation, one remaining mystery is associated with the iron metalwork on the south portion of the main roof, which was obviously designed to carry a heavy load. We know from photographs from the 1950s that any such structure on the Clintonville Station roof was long gone, and grainy aerial photographs of the station from 1939 also indicate that whatever was originally there was no longer present. Joe Montilla has observed that the strapping attached to the metalwork had been cut when the structure was removed, suggesting that the structure had been in place sufficiently long enough to have rusted in situ, making it impossible to dismantle by loosening the original bolts.
There are at least a few hypotheses for this structure. The first is that the structure carried a moderate-sized water tank, possibly for cooling the transformers in the main room below. Water-cooled transformers did exist at this time, and it's possible that the various heavy loads being placed on the Clintonville Station, including the Elgin line, the Elgin Belvedere line, the Fox River Valley line, the Elgin Trolley line, and the local farmers, all necessitated additional cooling of the transformers. The original air blast transformers would then have been replaced by the water-cooled transformers, along with pumping mechanisms to the water tank above.
The second hypothesis is that the metalwork supported one or more evaporative coolers on the main roof. The use of evaporative coolers in industrial settings had just started in the early part of the 20th century. Heat management of the overall substation was an ongoing concern for all of the substations, and may have especially hit hard the substations supporting additional loads, such as the Aurora and Clintonville substations.
As reported in the second video of this series, there was a 1911 reference from the Electric Railway Journal, which briefly stated, "To keep the machinery cool, a supply of water has been piped to the Aurora and Clintonville substation, and ventilators have been placed in the roofs of the Lombard and Maywood substations." The general reference to cooling all of the machinery, as well as the piping in of water, tends to support the evaporative cooler hypothesis, although it is a thin argument. In either case, once the load on the Clintonville substation decreased by the 1920s, the need for additional cooling may have ebbed, and the auxiliary cooling apparatus was more trouble than it was worth, and hence removed.
There are, of course, more mysteries to be solved and more questions to be answered about the Clintonville substation and the AE&C substations in general. But we hope that with this video series, we've established a good starting point as to how these structures functioned. As with all of our video series, these investigations are never fully closed. There's always more to be learned. With the Clintonville substation in particular, we suffer from a dearth of photographs and information, especially prior to the 1950 timeframe. So if you know of information or have photos that you can share related to the Clintonville substation, we'd love to hear from you. Please let us know by contacting us via the comments section below, or by our emails posted on the video trailer, or by contacting the Valley Model Railroad Association at vmrr.org.
We are, as always, indebted to the people who helped us with this investigation, most notably the folks of the VMRA, Joe Montilla, Jeff Oberek, and Bob Opel in particular. Their knowledge and insights helped this investigation enormously.
We hope you enjoyed this video and this series. To support us, please like and subscribe to our channel, and we hope to see you again in our next video series.